So I'm Garen Smith. I opened the lecture series last week talking a little bit philosophically about can science save the earth, thinking that the speakers to follow me are going to help us answer that question. I guess my response was, well, science can't save it, but it can certainly give us a reading on what's wrong with it and what might need fixing, and it's us that are going to have to do the fixing. And tonight we're going to get an excellent start on what might be wrong with the earth as Steve Running gives us a talk about our changing physical environment. So when I got the job of introducing Steve, I sort of felt like the announcer at a golf tournament who has to introduce Tiger Woods. I mean, we could spend 2 hours here going through the list of accomplishments and accolades that tonight's speaker, Steve Running, has accumulated. So I'm going to have to abbreviate it. I'm very familiar with Steve because when the Bee Project was really receiving heavy funding from the government, it was a neck-and-neck race each week as to who had more research support on campus. Was it the Bee Project or was it Steve Running? And so I've rubbed elbows with him a lot. As far as Steve's training go, he was trained as a terrestrial ecologist, getting his bachelor's degree in 1972 and his MS a year later from Oregon State University. I didn't know this until I got the job of introducing him, that he got his PhD in forest ecology in 1979 from Colorado State University. Now, I'm guessing he got that in the spring and made room for my wife, who started her forest ecology degree at CSU the fall of 1979. So I'm appreciating that he went out the door so that my wife could get her training too. His primary research interest is in the development of global and regional ecosystem biogeochemical models. Now, talk about integrating all of the sciences. We're going to talk about the physical changing in the world. So there's the physics, and we're doing biogeochemical models. So he's hitting on all cylinders here. So he looks at regional and global ecosystems, integrating remote sensing with climatology and terrestrial ecology. He's a team member for NASA's Earth Observing System, moderate resolution imaging spectroradiometer, and is responsible for the EOS Global Terrestrial Net Primary Production and Evaporative Index data sets. So net primary production talks about pulling CO2 out of the air and putting it into biological tissues. He's published over 220 scientific articles, so prolific author. Currently serves on the Standing Committee for Earth Studies of the National Research Council and on the Federal Interagency Carbon Cycle Science Committee. He's co-chair of the National Center for Atmospheric Research Community Climate System Model Land Working Group. These are long titles for these groups. And a member of the International Geosphere-Biosphere Program Executive Committee and the World Climate Research Program Global Terrestrial Observing System. Dr. Running's a chapter lead author for the 4th assessment of the Intergovernmental Panel on Climate Change and is an elected fellow of the American Geophysical Union and designated a highly cited researcher by the Institute for Science Information, which is how you really see how much of an impact you're having with your science. Now, with all these accolades, the other thing I'm very familiar with about Steve Running is that he takes time every spring to go over to Hellgate High School and participate in their Earth Week speaking festival, because a lot of times we exchange the microphone over there. So if you get invited back year after year to the high school, must mean that you're really able to engage your audience. So tonight we're going to get the pleasure of listening to Steve talk. I've never gotten to sit through one of his talks, so I'm really excited about this. So if you'll turn off your cell phones, we'll let Steve get started with his talk tonight. Thank you.
All right, that's going. I'm sure way too many of you were here last week and got to see all the chemistry experiments, and I don't have anything nearly that cool. And so I'm not sure how I'm going to do it, measuring up to that from last week, but I definitely have a lot to tell you about. And I better get started. Let me first start with the lights. Hey. Jeez. Yeah, I thought I had to do that. Okay, what I intend to do here is partially a bit of a tutorial on some principles of the climate and the Earth system, and then use that to talk really about what we now as scientists know about trends of global change and what is often just in the press called global warming. We're going to look at that a lot today and look at the kind of evidence that scientists have accumulated for that topic really progressively in the last 10 years. Starting with a bit of the tutorial, what's the difference between weather and climate? Well, weather is the short-term meteorology, really what's happening now for, say, the next week and maybe as long as a month. Whereas climate is the long-term trends of meteorology that we see over years to decades and even longer. And we had a real good illustration of the difference between weather and climate time domains back when Mount St. Helens went off. How many of you were here when St. Helens went off? Yeah, most of this audience was here. And it provided a real good illustration of how fast the atmosphere goes around the world. Because the air mass from St. Helens got here in something like, as I remember, six or 8 hours. And then about 10 days later, it came by again. It had gone all the way around the world, and we actually were seeing, now you couldn't really detect it the second time around without research equipment, but with research equipment, it was easily detectable, and it was a great tracer study that the air goes around the whole world in about 8 to 10 days. And that really is the primary domain of weather, is what the atmosphere is doing. Now I've got this really cool animation, and I hope these lights don't impede your ability to see this. This is a climate model that was done by some of my friends down in Boulder at the National Center for Atmospheric Research. And what I find really interesting about it is it gives us a little bit of a sense of the time scale of the dynamics of the atmosphere. And you see that as clouds move and these eddies spin off of the tropical bands and spin up into the high latitudes, and it really gives us a little bit of sense of how fast and how slow the atmospheric dynamics are. And I've always found I have to at least let this go far enough to get into the summertime, because you really see in the northern hemisphere the dynamics change a lot once you get to the summer. And that really, you think about the change from winter to summer in our latitude here is about 4 times as much solar radiation. So in other words, on June 21st, on a clear day, we get about 4 times as much solar energy as we do on December 21st on a clear day. Whenever it happens to be clear on December 21st, I got to admit, this is one of those hypothetical textbook definitions. But it gives you a sense of where the beginnings of our seasonal climate are, in that there's 4 times as much solar energy coming in June as there is in December. And it's that differential energy that then the atmosphere spins and stirs all around the globe. Now, one of the things you can't see here, because this is a flat screen, is a whole bunch of these dynamics are caused by the fact that the Earth's a sphere. And so the Earth is spinning around with this fluid, namely the atmosphere, enveloped around it. And so a lot of these circulatory dynamics are literally caused by the global circulation. We don't have to know very much more than that about these things. But this gives us a bit of a sense of the timing of our atmospheric circulation. And that turns out to be an important principle when we start going next to look at where the heat content of the Earth system is. And even though I study this all day, every day for decades, I only really understood this only about 4 years ago. I finally got it. When a paper came out in Science magazine that went through the heat balance of the climate system, you see up there on top the reference, and it pointed out something that is of fundamental importance. 90% of the heat content of the Earth's system is in the oceans. 90%. The atmosphere only has 3%. So climate doesn't come from the atmosphere. The weather for the next few days comes from the atmosphere. Climate dynamics come from the ocean because that's where all the heat content is. Even the glaciers and the polar ice caps, they're a couple of percent here and there. They're really nothing. It's the ocean and the circulation of the ocean that drives our climate system. And if you can understand that just conceptually, then you just saved yourself 20 years that it took me to understand it. That I guess it's probably something when you're a terrestrial scientist, you like to pretend that the oceans really don't matter all that much. And so it's probably I was trying to simplify my mind about earth science. And this one paper, finally, I got it. That we can't, in terrestrial science, ignore the ocean or we'll never understand climate, and that's why. All right. Now let's start with the principles of where the global warming issue comes from. And this starts with a single data record called the Mauna Loa atmospheric CO2 record. It's been called the most important geophysical data set of the 20th century. When you go into the National Academy of Sciences in Washington, D.C., there's two, on either side of the door, there's two displays of scientific research. One of them is the DNA helix, and this is the other one. That's how important this is, really, to humanity, because this one data set woke us up that humans were impacting the entire Earth system. If it hadn't been for this data set, we would have figured it out 20 or 30 years later. But C.D. Keeling, Charles Keeling, started this in 1957. And by 1970, we knew something was up. And it really was the awakening of the scientific community for global science in general, and particularly the issues of global warming. And in summary, what it showed us was every single year the CO2 in the atmosphere is going up. Every single year. Not one year has it gone down since they started measuring it. And this also is critical because he consciously chose to put this, measurement way the heck out in the middle of the ocean. He did not put it downwind from Los Angeles. That would have been pretty easy because he worked at Scripps in La Jolla. But he really wanted to know what the background atmosphere was like in CO2. And I'd have to say, having known Dave quite well, in the beginning, he didn't have any grandiose theories about global warming. He was just curious about the chemistry of the atmosphere and the fact that burning fossil fuel emits CO2, and I wonder if the atmosphere sees any of it. So it was a very innocent measurement, you might say, politically in the beginning, and it as I say, became the most important geophysical record of the century. And we now are off the end of this graph. This is a very nice graph, but it's a few years old, and we're now just short of 380, so we're now right about there. Okay, when the climate models, GCMs, and they're known as global circulation models, or sometimes people call them global climate models. When they attempt to simulate the climate, not the weather, the climate of the Earth system, one of the best ways to test your model is to start a long time ago and see if you can recreate the climate that we know has happened over the last, say, 100 years. So these climate modelers will start, will start back at the beginning of decent records, which is a bit before the turn of 1900, and they'll run their model up to the present. And when the leading climate models do that, the envelope of normal variability, you might say, the red line is the observations of the global temperature for the last, say, 100 years. And the temperature anomaly, I should say, the difference from a normal trend. And then the model sits in this envelope, you might say, and it does just fine until about 1980. And beginning in 1980, the observations veer up in the way you see here, whereas the model, if you don't tell it anything else, just keeps along within its normal trajectory. And it's only when they add to the model, as it says here, the greenhouse gases like carbon dioxide and sulfide aerosols, it's only then that they can recreate the last 20 to 25 year climate trend. And so these analyses suggest that our climate is clearly already reacting to our human presence and the greenhouse gases we're loading in the atmosphere. And what's more, it looks like we really started on a substantial warming trend in about 1980. And you see this in records over and over again. And we were all here in 1980. In fact, that's right when we were getting to Missoula. And I've never heard anybody give an explanation of what might have happened around 1980. But we see it in many, many climate trends that around 1980 the global climate headed off in a new trajectory that stays on to this day. And basically, the simple explanation for this is what's commonly called the greenhouse effect, and it really is, just as the name implies, the Earth acts like a greenhouse where the sunlight can come through the glass, and yet the warm long-wave radiation cannot return out through the glass, and so it stays trapped. And when your greenhouse warms up in the sunlight, in the very same manner, the Earth's atmosphere is warming up because of this partial differential of its energy budget of only a few percent, but that adds up fast, and we'll see how much it adds up here pretty quick. So the greenhouse effect as a basic theory of physics was suggested well over 100 years ago. So this basic idea has been around for a long time, from early physics. People hypothesized this sort of interaction in the Earth climate between atmospheric CO2 and temperature trends long before fossil fuel burning was an issue. They just, as a matter of some basic atmospheric physics. So what we're really seeing is just the manifestation of a well-known theory that's been around for a long time. All right, well, let's, now that we have a little bit of one of my students did this, and I don't know how to turn it off. And I'm pretty good at PowerPoint, but I'm not that good. And so they did this, and I don't know. I guess it wakes the audience up, which is probably important. Well, let's see what we know. Let's just take a look at climate trends, a variety of climate measures of the last 50 to 100 years. I like to emphasize this is not computer models now. This is all just direct measurements taken around in the Earth system. And the one you always read about in the magazines is the global average air temperature. And you see that over the last, say, 100 years or a bit more, the global average temperature has maybe gone up about 1 degree Fahrenheit. Now, we find that to be not a particularly interesting number because it aggregates so many different influences. So we like to look at a lot of more specific things in a lot more specific regions. So let's look at the U.S. Over the last about 100 years, just about the whole U.S. has warmed up in annual average temperature by something like 1.7 degrees. A little bit of the southeast has not warmed up, but you see the rest of the country has. Now, this is probably going to be news to most Montanans, but the climatologists claim that it's raining more. Raining and snowing more. And so when we look at the precipitation trend for the last 100 years, it appears to be going up. I think the number is something like 6.7% for the country as a whole. And again, this is stretched over a whole 100 years. We'll look in more detail at that a little bit later. So that's kind of the basic temperature and precipitation trends that we've seen in the U.S. But here again, a climate scientist would rather look at much more specific things than that. And let's take a look at the kind of things they want to look at. Well, first off, and here's back to my initial story about the oceans, we now realize that the oceans have this big, long, slow conveyor belt where warm water in the tropical regions loops up through, this is that North Atlantic loop that comes up and keeps Europe warm. And this entire loop, they think, takes something like 500 years for one water molecule, one theoretical molecule to make it all the way around this. Not that any single one would, but it gives you an idea. Remember what we were just talking about, the time constant of 10 days for the atmosphere to go around the world. And now we're talking 500 years for this ocean, this slow ocean circulation to work its way all the way around the world. And remember, water's got the big heat content, so it's this ocean circulation that is controlling a whole bunch and the majority of our climate trends with our current understanding. Now, when we start talking about ocean temperature, that used to be just kind of a fairly academic discussion until last year. And then all of a sudden it got to be dramatically more policy relevant. And this is off of actually our satellite. This is a picture of one of the hurricanes of last year, and really about the best hurricane picture I've seen in a long time. And basically, two papers came out, one in August and one in September, that for the first time correlated climate change trends with hurricane intensity trends. It had never been found before, and the conventional wisdom, actually when I gave talks on this topic 1 year ago, I would say it doesn't appear that there's any particular correlation between global warming and hurricanes. Now, a year later, I'm telling you something different because of these two papers. And these two papers probably have had more impact on this science than about any papers in recent memory. And they both tell effectively the same thing. Basically, the first paper that came out in Nature came up with a potential destructiveness index. And basically that combines the wind speed of a hurricane, which is when they talk about category 3 and 4 and 5, all they're talking about is wind speed. Well, this adds together the wind speed, the overall area of the hurricane, the time duration that the hurricane is pounding away, and puts all these things together into a summary measure of how destructiveness it is. And what you see if you look a little bit is here right around 1980, you could imagine the first 30 years here not showing a whole lot of trend, and then a trend up that exactly corresponds with the ocean temperatures, the sea surface temperatures that are the dotted line is sea surface temperature, and the dash and the solid line are the destructiveness index of the hurricanes that occurred each year. This was followed about 2 weeks later by a paper that in Science magazine that basically showed that this is for, I'm pretty sure, the Atlantic. An increase in category 4 or 5 hurricanes. I mean, nowadays everybody knows what that means. Probably a year ago, hardly any of us knew what a category 4 hurricane was. Basically, he found no increase in category 1, 2, and 3 hurricanes, but an ominous increase in the real big ones. And again, related directly to ocean temperatures. And in fact, when we look at that ocean heat balance, we have a lot of evidence that the ocean temperatures have been going up. And this is sea surface temperatures, or SST, by all of the different ocean basins around the world. And you see a clear trend. It isn't very much. It's only a few tenths of a degree. But remember how much energy water holds. And so a few tenths of a degree times the whole Pacific Ocean is a gigantic amount of energy. And what we're now seeing is, we think, the manifestation of these higher ocean temperatures in hurricane intensity. And remember, neither of those papers had the 2005 season in them. So the biggest season in history isn't even in their data sets, and they still saw these trends. Now when they add 2005 onto their trends, it's going to bump it up obviously even higher. The bottom line of this is that the climate scientists really can't see any reason that we aren't going to be having more and more of these kind of hurricane seasons in the coming decades. And if you lived on Key West, I'd be kind of nervous, because we just think there's going to be more of these coming. The trends and the physics that we understand clearly suggest that. That doesn't mean every year's going to be bad, but it means little by little there'll be more and more big hurricanes of the kinds that we saw just last year. And this is the sea surface temperatures for every ocean on Earth measured by a satellite since 1979. And you see every single ocean on Earth is warming up. One of the things that warming water does is it causes sea level to rise. Now this is people that think about this a little bit, they think that sea level rise is all because of glaciers melting. And that's about 2/3 of sea level rise is coming from melting polar ice caps. The other third of it is just simply that water expands as it gets warmer. And so as we're heating the ocean, the water's expanding and the sea level is rising, and that goes on top of any melting of glaciers or polar ice caps, which we're going to look at soon. And so this is the trend in sea level rise over the last century. And you can see on the order of about 20 centimeters, which, especially sitting in Missoula, Montana, doesn't sound like a big deal, does it? Oh well, sea level 20 centimeters. I like to joke to my audience, if you haven't been to Venice, Italy, I'd go quick. Because they're already having flooding in Venice, where if you show up at the wrong time, you get knee boots to wear. And through the famous squares through the middle of Venice, you have to slosh around in knee boots, because literally there's water right into the center squares of Venice already. All right, now I just said something about the polar ice caps, so now let's take a look at those next. Now we've looked at the ocean for a while. What's happening with the polar ice caps? I've got a quiz that probably a few too many of you have already heard this talk and know the answer to the quiz, so you don't get to answer. How thick is the ice at the North Pole? Anybody give me a guess?
Average? What?
Oh yeah, average. I mean, plus or minus a couple of. How thick do you think the ice is at the North Pole?
3 feet.
Is it located where there is ice at the North Pole right now?
I heard at least somebody say 100 feet, and that's back before I saw this, my own talk. That's about what I thought it would have been. Oh, it's got to be like 100 feet thick up there. It is the North Pole. Well, to start with, here's the answer. And the reason we know this answer is because of the nuclear submarine fleet. In 1957, I think it was, we launched our first nuclear submarine, and they've been cruising the Arctic Ocean ever since then, and the U.S. Navy has been taking tens of thousands of ice thickness measurements all around the Arctic ever since 1957. Well, when they first started doing this, the thickness was about 3 meters, or about 10 feet thick, at the North Pole. I mean, I guessed 100 feet too, so whoever guessed that, don't feel bad. That was about what I figured it had to be. But the big issue is it used to be 3 meters, and in the 40-something years since they've been measuring, it has gone down 1.3 meters in average thickness of the whole Arctic ice cap. This is an average of tens of thousands of measurements. It isn't just 1 point, from all over the Arctic. That's a pretty big reduction. A 40% reduction, and actually this is a nice graph, so I keep using it, but this is about 4 years old. If I was to update this graph, it would be more. Because what the satellites are now showing us is the melting rate. Can you see this? This is Alaska right here. And this is North America, Hudson's Bay. This polar projection's a little bit weird. But this is where they're showing, the satellites are clearly seeing accelerated melting all around these margins. And they're expecting that within a couple years, they're going to start ship traffic that'll come through here, and they won't have to go through the Panama Canal. Going between Asia and Europe, they'll cut the corner right over the top here. And so don't say there aren't a few good things about global warming. There's some shipping people that can't wait. Now, one of the things that I learned when I went to Barrow, Alaska, which Barrow sits right about there. Prudhoe Bay, incidentally, sits right about there. You know how you get a pickup truck to Barrow, Alaska? Well, you'd have to fly it otherwise. They drive them up the haul road from Fairbanks to Prudhoe Bay, because anybody can drive up that. And then they wait till the winter when the ice forms and they make an ice highway. And it was really interesting to hear about it. So they make this ice highway. I guess it has stop signs and probably not too many traffic lights. But basically they have an ice highway over to Barrow, and that's when they bring in all the heavy stuff, is during the winter on this ice highway. It's 3 times cheaper than any other way of getting big stuff into Barrow. The problem is, yeah, obviously the ice highway is only good for part of the year, and that period of usable safe ice has gone down something like 6 weeks in the last 30 years. It's 6 weeks shorter than it was when they first started doing this, when they put the Prudhoe Bay and the haul road in for the pipeline. So just in these 30 years, they're measuring this dramatic shortening of the amount of time that they have this cool ice highway. I was quite interested. It'd be dark up there. It'd be dark and cold, and you just drive. Imagine just driving off into the ice. I guess you'd want to have a good GPS with you, that's for sure. All right, so at any rate, you're seeing some edges that are in a melting trend. Here's the aggregate for the whole northern hemisphere. Again, we take this with a microwave satellite that was first launched in 1979, and we see a progressive trend. This is the area of ice coverage, and you can see it's gone down by about 1 million square kilometers over these 24 years. And to just give you an idea, Montana is about 0.4 of a million. So it's gone down by about 2 or 3 Montanas worth of area in the last 25 years, the Arctic ice cap area extent. And remember, the slide a little bit ago said that the thickness, so we've got the area coming in and the thickness getting thinner. Same time, very consistent measurements. Another look at effectively the same data set graphed differently, so we'll continue. Now, as you might imagine, glaciers are retreating in the same sort of pace. This is, I can't read this. I'll bet you can't either. But what it is the name of dozens of glaciers, 67 different glaciers in Alaska, and this is the time period from 1950 to either 1995 or 2001. So it's about 50 years, and you can see that there's a couple here and there that are getting longer, and every other of the 67 glaciers is retreating. And in Antarctica, the same story. This is a time interval starting from the 1940s and this going to the 50s, and as we come here to 1995 to 2000, you see the cumulative Antarctic glacier mass is on a similar sort of trend downward for the last about 30 years. I've actually been to this glacier myself. This is over in North Cascade National Park in Washington, and I wasn't there in 1928. I was there in 1968 and walked to right about there. Now, I wish I could go up there again, because this is what this glacier looks like now. And of course, around here we all know about Glacier National Park. And one of my good friends is the park scientist up there, and he says they already have the name change planned, because in 30 years there'll be no more glaciers, and so they're going to change the name to Glaciated National Park, because it's a glaciated landscape, but minus a minor detail that there's no glaciers left. And so this is a look at Grinnell Glacier, the most famous one from 1850. You're looking down. This is a real weird aerial photograph that it takes a while to figure out. But you're looking down and you see the area from 1850 and then to 1993 and then, of course, now into 2003, shrinking virtually every year. Another look at the cryosphere. You'll notice that an awful lot of the evidence that climate scientists like to look at is the cryosphere, snow and ice, because it's easy to see. It's easy to measure. And so the reason that we find that looking at these sort of measurements is more illuminating is because you really can detect trends a lot quicker, and we also have very long time series of some interesting things. This is permafrost up in Fairbanks, and any of you that have been up around there probably were told that for a long time, with permafrost, with the whole soil frozen under you, that's a free foundation. What do you need to pour a concrete foundation for if you've got solid ice that's there for nothing? And so they, for decades, built houses using the permafrost literally as a free foundation. And what's now happening in Fairbanks is that at about 10 centimeters depth, 4 inches, it's now not even freezing in the wintertime, and even down to a half meter. It's thawing every summer. And there's houses that have now had to been abandoned in Fairbanks because their foundation literally just kind of melted it out from under them, and they're just all cockeyed. Like, imagine one corner of your house just settling. The corner of my house has settled a half inch, but they've had 3, 4, 5 feet that this house, they just kind of tip over, and they drove me by a couple of the more spectacular examples of that. Another measurement that we've taken for a long time, we being humanity in general, is the time of icing, river freeze up, and then river breakup. This is important for river transportation, and so we've got some amazing data sets that start back in the 1840s. And this is some of our longest cryospheric data, are these river ice up and then breakup trends. And probably a lot of you know the famous contest they have in Fairbanks every year, where everybody puts $5 into a big not a lottery, it's basically, what do I want to say, into a contest. And whoever predicts the exact moment that the ice starts to break wins the whole pot. And this pot's $100,000 nowadays. It's big money from everybody just putting in their $5 and putting in their guess of when the river will break up. And what this is, and this has way too much data to follow individually, but these are rivers from all over the world, and this is their freeze date in the fall, and then their breakup or date in the spring. And the trend of all these rivers all around the world collectively are freezing up on the order of maybe a week to 10 days earlier, or later, excuse me, in the last 100 years. But the big thing being that they're breaking up on the order of 2 to 3 weeks earlier in the spring. And that we're going to return to that topic here in a little while. Now, one of the theories in climate science is that global warming is going to accelerate the hydrologic cycle. Well, what the heck does that mean? It means that water from the surface, the ocean and the land surface will evaporate faster, and that will get more rainfall as a result. And you saw for the U.S., a suggestion that maybe we are getting more rainfall. What they've now figured out is that more so than a change in overall rainfall, it seems like when it does rain, it's more intense. When a greater fraction of the rainfall events, this is just for the U.S. Right now, a greater fraction of the rain events turn out to be big gully washers rather than just kind of nice, polite rain. And so this is kind of a complicated interpretation of this graph that shows that it used to be, maybe 9% of the rainfall events were more than 2 inches. And now that's snuck up to more like 11%. Now this isn't the kind of climate stuff that came from us. We haven't had a 2-inch rainfall event in Missoula for, I think, ever since I've lived here. And so this is really other parts of the country. But it does give us some suggestion of increasing hydrologic intensity the way the climate theories would suggest. Well, I finally get to my end of Earth science, and that's the biosphere. Are the ecosystems showing any response to all these changing climate trends? And it turns out that we do have some evidence. This is just spring bud bursts, right? What we call in science the phenology of the trees. It's simply just the observation of the date when the buds burst on the trees. This is Notice Aspen up in Edmonton. They took a few years of data way back at 1900, and then, I don't know, they lost interest for a couple of decades, and then they started it back up. And you put the whole trend together, and you find that bud burst in the spring is about 3 weeks earlier in Edmonton than it was 100 years ago. There's some real interesting phenology data sets rattling around the world. The favorite one that I know of, and it's more of a sociological study than a climate study as far as I'm concerned, there are some estates in Britain that have been in families for hundreds of years, the same family for hundreds of years. And there's one particular one that there was a big paper in a scientific journal written up on its data record. For 240 years, this family has recorded all sorts of seasonal phenological events on their estate. The sighting of the first robin, budding out of the roses, just a bunch of observational things, the date that it happened. And you go, well, that's okay. Imagine trying to get your grandchildren to take the data right. For 240 years, they've impressed upon their grandchildren, great-great-great-grandchildren, this is important, you do it right, you observe this and you write it in this here little book. And I find that just an amazing bit of family psychology. I mean, how many is that? 10, 12 generations have been taking these simple observations on this one spot. And it turns out that's it's virtually, not virtually, it's the single longest record I know of any kind of biospheric observation by this family on their estate. And I don't know, I think that's kind of cool. And it's showing the same sort of trend, and we'll see more evidence of this. Here's the growing season length in Alaska over the last about 50 years. Has gone up on the order of about 2 weeks, and this is just based on their climate statistics that they take at their weather stations. If you look at the U.S. as a whole, now this is a bit of a tricky map, because this is days per decade of change in frost-free length. So we have 1.7 days per decade for about 5 decades. So you multiply that by 5, and we're on the order of something like 8 days increase in frost-free length in the northern Rockies according to this data set. And you see all around, particularly the western U.S., but really the entire U.S., the number of freezing days is going down, and the number of days, the growing season effectively, this is good news for the gardeners, is going up. And when we looked at our satellite data for the last 20 years in our lab, and attempted to do this kind of a similar sort of analysis conceptually for the whole world, we came up that this is the net primary productivity that you were reading off. The net primary productivity of the world, we think, has gone up about 6% over the last 20 years, up to about 2000. And particularly because in these high latitudes, it is just getting warmer and the growing season's getting longer. And then also in the Amazon, we think it's getting less cloudy. And so between those two factors, and we can't really, particularly the Amazon cloudiness, we know it's occurring from ground records. We don't know why. But we think that overall, the biospheric productivity over the last 20 years has gone up some. Now, this is exactly what our job was for NASA. And so this is, they do really cool animations. And so, because this isn't the real picture. Remember, this is not an astronaut on the space shuttle taking a picture of our rocket as it took off, but it really gives you an idea of how these satellites go up into space. And all that flies off. And of course, incidentally, becomes space junk. I was reading just a few weeks ago that we are getting into a serious issue of too much space junk. And, you know, if one of these babies hits something, it's all over. And so we're getting a little too much junk up there because they all tend to want to be in the same orbit. They aren't randomly dispersed around the Earth. Well, our job for NASA was to take this data set. And so this was the first 2 years of data from our project here. This is numbers crunched over in the science complex for the weekly biospheric productivity of the Earth. This has never been done before. And it gives us a look at the biosphere in action week by week through the year. Now this is through 2002. We just about 2 weeks ago finished all the way through 2005. So these animations are kind of hard to put together, so we haven't put the whole 5-year animation together yet, but we will be soon. And what you really see, you finally get a sense of the Earth as kind of this single functioning organism. Almost, you know, the old Gaia hypothesis was about the Earth as a single organism. And this is, to me, the best way that I've ever seen to get a sense of the dynamic biosphere in action. And as I say, this isn't a computer model. These are direct observations from the satellite with a little bit of computer processing, let's call it. We won't call it a model. And so that's our job for NASA, is to continue to monitor the entire global biosphere to look for trends in biospheric productivity. So that's been our job for about the last 15 years and continues to be the primary job of my lab here at U of M. Well, let's look at some other aspects of biospheric impact and see what's being found. Let's talk about coral reefs. A topic that I'm not much of an expert on, although I do like to go snorkeling when I can. I'm always impressed by that water temperature, 85 degrees. About the best Flathead Lake ever gets is 75 degrees. And so to have the whole ocean at 85 degrees is almost beyond what I can really internalize. And yet it's at about that threshold that coral reefs, as they call it, bleach out. And what they're finding now in the last decade is coral reef bleaching problems all over the world. Now, I will say it's more than just ocean temperatures. Coral reefs are in trouble for lots of other things. Nutrient runoff from the land, physical damage from overfishing, I mean, the coastal development, there's a lot of things. Everybody wants to hang around coral reefs, unfortunately, and they're paying the price for it right now. But we're seeing a degradation of coral reefs globally that's really pretty shocking to understand that it's really global. I did get out on the outer barrier reef just about a year ago, and I'm at least pleased to say when you get way out there, it still looks just unbelievable. So they aren't completely ruined everywhere, but certainly the closer they are to population, the more damage they've occurred. Now, unlike the terrestrial biosphere, we think the ocean productivity has been going down. And so this, again, are some satellite data sets from about the last 20 years. And they find the ocean productivity. These are all different basins, the South Indian and South Pacific. And so this is basically going down. A few of them going up the equatorial Indian Ocean. North Indian are going up a little bit, and most of the rest of the oceans are going down a bit. Now, increasing ocean temperature shouldn't directly cause that, but well, I probably shouldn't say anything else because I'll probably say something wrong since my ocean friends assure me I really don't know very much about ocean science. So I'll just let the data talk and we won't add any extra interpretations on that one. Of all the global change issues, the hurricane intensity is a big trump card. That got an awful lot of politicians' attention, more than anything that's come out in 5 years. The other trump card that we hope doesn't get played is in global human health. If we have some sort of a big-time global epidemic, then that is climate triggered and that climate takes us into, then boy, everything else pales in significance. It really makes you not want to fly around on international airplanes because every propagation mechanism the global epidemiologists talk about starts with airports and international airline travel. And it's getting now, so I want to go on the airplane, you know, like Michael Jackson with a, you know, with a white gloves and hood and all that. Maybe he's right after all. Because unfortunately, that's really the difference between global epidemics of 60 and 80 years ago when you crossed the Pacific by ship and it took weeks. And, you know, what does it take to fly from Hong Kong to Seattle? I think it's 10 and a half hours, something like that. And so we, and I say we being the global science community, if there's anything we're most immediately nervous about is the potential of something big popping out in a global health epidemic. Now, having said that, we're hearing a lot about bird flu nowadays, and there could be some serious potential there. We don't see any climate signal in that. We don't see climate changes having anything to do with bird flu. So what I'm really referring to here is global epidemics that might be climate triggered. And we don't really have evidence of any real climate triggers to any of these kind of problems. It does bring up the future potential, particularly as climate warms in the lower latitudes, is that the subtropics are inching north. The subtropics defined as where it doesn't freeze at all year long. And that's the maximum and that's the minimum. I hope you can see that pretty well. Now this is the graph that really blew us away when we first put it together. The March temperature. And what is it today? February 21st, so we're 8 days away. The March temperature has gone up 6 degrees in the last 50 years. That really is just remarkable bit of climatology. 6 degrees in the last 50 years. Clearly, our winters are ending earlier than they used to. And in fact, finally, we have clear evidence that when the old timers said it used to be a lot worse, they're not kidding. It really used to be a lot worse. And we really are seeing this in temperatures, that winter drug on an awful lot longer than it does now. And the fact that we can look outside and see our hills, our local hills already clear of snow is kind of a manifestation of this exact graph. The number of days that freeze has gone down by about 2 weeks. So in other words, our gardening season is a couple weeks longer. When we first got here in '79, I planted an apricot tree because I kind of like apricots. And it suffered along for about 4 or 5 years and finally croaked. And I'm figuring I better plant another one because I think it may make it this time. Because this is a measurable improvement in our gardening climate. Now what we just took a look at, now I would hope your inquiring mind would have been sitting there thinking, yeah, that's Missoula, but is this really happening around the whole state? But I asked that question first and I have the answer. And I'm not going to show you all the other sites, but here's Billings. Almost the identical overall trend of a couple of degrees warmer in the last 50 years. And almost identical also this March warm-up. About almost 6 degrees warmer in March in the last 50 years. Now, we have from just over the border, one of my Canadian friends that's on one of these international commissions with me just sent me their measurements that I won't crawl through these in detail for you, but basically what you're seeing, of course it's degrees centigrade to wake you up, do a little translation on the fly, but they've done the same sort of analysis through some of their weather station records and are coming up over a 100-year period with pretty close to the same types of trends up there. Precipitation up a little bit on most of the sites. There's snowpack down in 4 of the significantly down in these 100-year-long trends. And so maintaining the precipitation, but more of its rain and less of its snow than what it was 50 years ago and more. This is one I'm keeping an eye on, and our lab was just about 3 weeks ago finally authorized as the state climatology office. We asked 3 years ago, no funding, just for the authorization, and we finally got it from the governor's office three weeks ago. So we have this nice state climatology website, and we're putting all these kind of graphics up there. And one of the things I'm watching for is to see what kind of changes in humidity we have, because we know around the country as a whole that overall the humidity is going up. And I've yet to meet anybody that thinks that's good news. Now, if you're a plant, it's good news, because plants really like higher humidity. That's the first thing you do in a greenhouse is increase the humidity and the night temperatures. But for us walking around, high humidity is nothing that we're looking forward to. And what they find up here in the Okanagan is a downward trend in relative humidity, and I'm really going to be curious to see if we see a similar trend in Montana. The problem is humidity data is hard to come by because it's a hard measurement to take. What we do know, and this is exactly consistent with those warmer March temperatures. This came from a friend that's over at the University of Washington's Climate Prediction Center. And he just came up with an analysis of this April 1st snowpack. Basically all the SNOTEL stations all around the western U.S. where maybe some of you, I always wanted to get this job. I never got this job. You get paid to ski out and put the pole in the snow and measure the snow depth. Why couldn't I get jobs like that? And so they looked through the 50-year record of those snow survey stations, and we've had, on average, the red dots are a decline, the blue dots are an increase. You see all around the Northwest. The average of the whole data set is a 45% decrease in the April 1 snow water equivalent. And you know, we've already seen Marshall Mountain go out of business. My daughters grew up skiing there, and I'm not all that old, thank you very much. And so we're already seeing the very local manifestation of us having a shorter skiing season. And the seasons pass at snow bowls becoming really a less and less viable financial decision, I'm sorry to say. Even though I wish them well, I ski there myself. The blunt fact is, it isn't very often they're still open in April anymore. And 20 years ago, they would be. What this is causing then is snowmelt to come off 2 to 3 weeks earlier, which means all the river flow is coming off 2 to 3 weeks earlier, and it's starting to really change our water management. And yet I'm not so sure our water managers are paying attention to the fact that this is a clear and very obvious trend to the climate scientists, that the runoff is starting earlier, it's peaking earlier. If you're going to use that water for irrigation or to fill Flathead Lake, for example, for recreation, that water's got to be captured earlier because there's not as much up there come April as there used to be. So this is really the foundation of some of our water management issues that's starting with these earlier, these warmer March temperatures, melting snow earlier. This is an awful lot of why our blue ribbon trout streams every few years have to be closed in August. The summertime low flow has gotten so low that they've got to pull the fishermen off because the water temperature's gone too high. And all of that starts with these higher March temperatures. And so we really are clearly going to see more and more of these kind of years where that minimum flow in the summer just turns into a trickle, and that all the river recreation is probably going to be impacted on these dry years just more and more. But this is the big one. And when my friends talk about hurricanes in the southeast, and I think about, well, I'm not too afraid of hurricanes. I'm not too afraid of sea level rise. But what am I afraid of? Starting in 1988, the big Yellowstone year, we've had 5 100-year fire years. 1 in 100 years, and yet we've had 5 of them in 17 years. We've done pretty well the last couple summers. It's not been too bad, but that's not climate. We've got to look over the longer period. And what we're clearly seeing is a suspicious, in my mind. This isn't, this wouldn't, I'm not sure if this would hold up in court yet. And in fact, I'm writing this for the Intergovernmental Panel on Climate Change, and it might end up getting reviewed out. We'll see. But I sure find in the Northern Rockies that 5 big years out of 17 is not a 1 in 100 year probability. And that's what we're starting to see. In Canada, they've already quantified this. And this is the area burned of wildfires across Canada related to their observed temperature trends. And here again, right around 1970, 1975, it just kind of, we see again this look that, that something seemed to start going off in a new trajectory. Well, where do we think we're going? Everything I showed you now for the last, I don't know, 50 slides or something have been measurements of what's occurring right now, the trends that we've seen over the last, say, 50 years. Well, this is our best local prediction of where we'll be in about 20 more years, is another 2 degrees warmer. And the models are very poor on their hydrologic cycles. So they say that we'll get 7% more precipitation with that. We as climate scientists know this number's pretty solid, but this one isn't so solid. And I think that's going to make a big impact on what our ecosystems look like 20 years from now. Because if it gets 2 degrees warmer and we don't get any more rainfall, you can imagine what it'll be like. And if we do get rainfall, it'll just, our climate will tend to get more and more like Portland. And so when I try to summarize where I think the Montana climate's going, this is it. Shorter, milder winters. This winter is yet another example of that. Every year I keep thinking, well, maybe we'll have a big winter this year and kind of tilt the average back. And boy, year after year is now ticking by and they're not. I'm a big fan, incidentally, of extreme temperatures. I was really hoping we'd break the minimum temperature record on Saturday night. In fact, I stayed up all night just chanting. Well, no, I didn't stay up, but I was, the next morning I got up really kind of excited to see if we broke it. And partly just because when you're a climate nerd, that's the kind of thing you think's cool. But beyond that, we understand that really low temperatures are what I like to call an ecosystem cleansing agent. It cleanses out all sorts of tropical bugs that think they're tough enough to come to Montana. And a couple of 20 below zeros, we know from the entomologists and pathologists, it really does work. And so you don't need to have months and months of 20 below zero. You just need a couple here and there. And so I was kind of hoping we'd get couple. I guess in Seeley Lake they did just quite fine over there. But we kind of ran short here. Okay, we've seen earlier snowmelt. Imagine if in 30 years the snow melts 3 weeks more early. Then you're getting into this time of year the snow being gone. So the trend we're on now just extrapolated forward to 30 more years, and we're going to really have a snow season that starts maybe something like mid-December and ends by early February. But boy, are we going to have a gardening season. And so absolutely the gardeners are going to win on this as long as they're irrigated gardens. Because the flip side, the summer side of all this, the question that I'm really attacking diligently right now is to try to understand, is it going to get drier or wetter? We know it's going to get warmer. It's not so clear whether it's going to get drier or wetter along with it. And so there's some interesting ecological puzzles that come along with this. Certainly you can plant crops earlier, and we know forest growth rates are going up so far around most of the world. In fact, forest growth is not accelerating a lot, but at least it's not going down. I think we're probably getting less deer and elk winter kill, because where they really die is they get wiped out right about this time of year, the end of the winter, in those really punishing storms late in the season. And I think because of pointing this out, the Game Commission should give me an automatic moose tag every year, because that's, that doesn't cost them a thing, and I'm providing them a valuable intellectual service here that they probably haven't noticed before. But I really think it's going to be important to factor this in to what they think about the population cycles of our game animals, because I really don't think I know we don't have the same seasonality of climate that we did 20 and 30 years ago. I just showed that to you, and that certainly is going to be reflected in some aspects of the population cycles of our game animals. I'm kind of curious, what do hibernating animals do when it doesn't get cold enough? We have grad students, the professors never do this, we have grad students that crawl in the bear dens and take their temperature while they're sleeping. Well, what if it isn't quite as cold as they thought it was? And so hibernating animals are, the hibernation cycles controlled by temperature. And as our winters get milder, I really wonder what they'll do. It may not hurt them any, but it certainly is going to be a change. We are really curious of whether we're in for more big insect disease outbreaks in the forest, like these giant mountain pine beetle epidemics that we've had here. We've had those before, and we wonder whether those are going to get more common. It's really hard to tell so far. Definitely our aquatic ecosystems, when the river flow goes down, the water temperatures go up. When the water temperatures go up, the dissolved oxygen goes down, and then the fish really are hurting. And so as our late summer river flows go down, that's definitely going to be a problem for some of our aquatic habitat and things like fishing recreation. The other dimension of this whole issue that I think the U.S. is still doesn't seem willing to grasp correctly, is this is clearly a global issue. We can't just go this one alone. This is a graph that's meant to illustrate that we're in the tailpipe of China and Southeast Asia. So no matter what we think that we can just go do what we want, if we don't get China, India, and those countries to be cooperative about climate change and global pollution, we're going to just literally be breathing their tailpipe. And in fact, some of the summer days when we have kind of an orange sunset, and I've asked some of my atmospheric science friends, what's the deal going on? Are there fires up in Washington? No fires. We now have followed by satellite giant particulate smog clouds that start in China and come all the way across the Pacific. So we literally, right here in Montana, are seeing pollution from China. And so to me, I'm not trying to point a finger at China. I'm trying to make the point that we're all in this together, and the U.S. is going to have to cooperate with every other country in solutions to this, and so far we're not doing very well. This is a picture that came off our satellite. Our MODIS is our satellite. You can tell I spot all sorts of interesting things that our satellite does. This is the aircraft contrails over the southeast U.S. for a single snapshot to give you just some sense of the atmospheric loading that we put on Earth. And two statistics that relate to this. One is that big airports like Atlanta have 1 million flights per year. 1 million! I used to think 1 million was a big number. This is out of one airport. I thought I was wrong. I sat down and calculated it. And it's like a flight every minute, 16 hours a day. Go add it up. It comes up to 1 million flights a year. Atlanta has 1 million, Chicago has 1 million, all sorts of our airport. 1 million flights a year. And this is the result of it. The other point I'll make on this, September 11th provided one of the finest atmospheric chemistry experiments ever done. And I remember at the time, along with all the shock of that event, thinking that, boy, having all the U.S. commercial aircraft grounded is going to tell us something. You know what? Within 1 day, they could measure the difference in the atmosphere over the U.S. 1 day. It was detectable with the research instruments how much less aerosol coverage. I mean, think of this, all of that would be gone. And so we know just aircraft travel alone has quite an atmospheric loading that this picture just gives us a sample for. And so this was the cover of National Geographic about a year ago. And it's interesting to have been a climate change scientist for the last 20 years and have watched this climate science develop and watched as we progressively have documented all these global warming trends and impacts. And it really appears that our climate science is going to get virtually overwhelmed by the final solution. Basically, this is the discovery rate of oil since 1930. It peaked in about the 60s. And you'll notice, and here's the oil production and consumption. And you'll notice that since 1975, every year we've consumed collectively more than we've found. And how much longer can we do this? Well, even the oil companies get it. This is in the inside cover of this week's Newsweek. And in fact, I've seen it a lot, and maybe I notice things like this, but almost all the oil companies in their Olympics ads and Super Bowl ads and all that and stuff, they're not bragging about their oil. They're all talking about basically this graph. Because what we see, even apart from the climate change issue, is that the end of easy oil is in sight. And there is just book after book after book coming out analyzing this every which way. Now, I can't even read them fast enough. And these aren't climate scientists at all. These are economists and petroleum geologists and people like that are saying that these two trends, something's going to give. And something's going to give. It's not a matter of if, it's a matter of when. And it used to be they talked, well, probably 30, 40 years from now we're going to have to get serious. And the demand for global oil, particularly from Southeast Asia now, has caught up enough that now as they call it, the peak oil production date, there's now various predictions that it might have happened literally last Thanksgiving, one guy says. and he's a petroleum geologist and knows a little bit about it. So it's just a matter of when in the next few to at most 20 years that oil production globally will peak, and then it's nothing but a downhill slide. And you know what happens when demand exceeds supply on anything, don't you? To price. And we see nothing but, who knows, $5, $6, $7 a gallon gas in our future. Who knows when it'll start? If I could predict that, I wouldn't be hanging around here. Oh yeah, I still would actually, but I'd be some, fat consultant lobbyist or something. So nobody can say exactly when, but we're really only arguing a couple of years here and there. This is going to be the biggest transformation of human society since the Industrial Revolution. And this graph just shows that it's on its way. And so far, the country that's in last place is ours in thinking about this seriously. And so the demand curves for global oil keep going up, and yet we already know the supply is not going to be there. And that's, of course, if nothing else goes wrong in countries like Iraq and Iran and places like that. And what's the chances of that? What we're really arguing about climatologically here, this is the climate trend of the Earth's surface for the last 1,000 years. And remember that envelope of natural variability that we showed, and here it is for 1,000 years. The temperature data got better here for a while, so it got a little tighter. And here we are right now. So we've left the envelope of natural variability for the Earth's climate of the last 1,000 years. And basically, we know that at best, we're going to end up a couple degrees warmer than we are now. And if we really do nothing, and if maybe the oil supplies will solve this, maybe we can't get to here. The climate models run us up to about an 8-degree warming in 100 years if we continue to just go bananas. What you see from the economists is that maybe isn't even possible anyway, so maybe we'll be saved from ourselves. The end. That's all I have to say.
Well, thank you, Steve.
On this topic, it's usually bad to take questions, but I think it's my job, so I guess.
And I'm going to run around with the microphone because remember we're putting these sessions on tape and we want to capture your question as well as Steve's answer.
It looked like in the interior of the southeast, at least in the United States, that there's been the least change in the data. Is there any hypothesis or theory that goes along with that?
Believe it or not, we think the humidity's going up in the deep south. Doesn't that sound lovely? So we think the humidity is going up, and remember the heat capacity of water is so high that when you have more water in the atmosphere, it holds the temperatures from changing either up or down as fast. So if you think it's good news that if that's the way you keep it cool is by having the humidity go up, then I recommend you all move to Atlanta and send me a postcard.
You talked about, and other people have talked about, how there's a natural cycle for things, and you talked about the temperature going up in Montana. How much, and I certainly believe in global warming and stuff, so that's not why I'm asking this, but how much of a cyclic change are the temperatures rising attributable to, or how much is it, global warming?
There's a variety of pieces of answer I can give to that. We know that the atmospheric CO2 has been higher in the past. During the dinosaur age, it was higher than it is now, for sure. We don't think that atmospheric CO2 has been this high for approximately 1 million years. And we trust, we get most of this information from ice core data. They drill ice cores in Antarctica. I think the new record is 5 miles deep. And they analyze the bubbles in the ice. It's really pretty cool science. So they get this core out, and of course 5 miles a core. And then they take that and they can analyze the bubbles and just learn really precisely what the atmospheric chemistry was when that bubble was formed. So we know that the atmospheric CO2 has been higher in the past, but it's been the very distant past. Probably the best way to think of the issue here is that the carbon in fossil fuels took something like 100 million years to slowly be sequestered and turn into oil and coal and gas, right? We're burning it in 100. So take any kind of a dynamic system you want. And here you have a rate constant of 100 million, and here you're reversing it in 100. So you've basically accelerated the whole show by a factor of 1 million. And that's what we're doing with the carbon cycle of the planet, is we're releasing that carbon that slowly went into oil and gas, from all the primordial swamps that got covered up and turned into oil and gas. We're digging it all up and burning it and putting that carbon back in the atmosphere in 100 years that went in 100 million. And so nobody's arguing that the Earth didn't at a previous time wasn't warmer, or that atmospheric CO2 wasn't this high either. But nothing's ever happened anywhere as near as fast as what we're forcing the Earth system now.
Somewhere I read that if the temperatures change in the oceans enough, this cyclical pattern of the ocean movements was going to change, and there may be a big effect of that. What is your opinion on that, and what do they think?
One of our most famous Earth system scientists, Wally Broker at Columbia University, about 10 years ago, almost as kind of an offhand joke, he was talking about the North Atlantic thermohaline circulation that basically brings Gulf ocean water up the east coast of the U.S. I mean, everybody knows that the ocean temperature off of Maine is warmer than the ocean temperature off of Oregon. Okay? And so we've got all this warm water goes up into the Arctic and then sweeps down to Europe. And the same thing. Over in Europe, it's way warmer than it's supposed to be for the latitude. I mean, way warmer. You know, up in Stockholm, they barely get enough snow to ski on in Stockholm. And it's higher than Edmonton in latitude. So Europe is benefiting from this thermohaline circulation of the North Atlantic. And Broker just kind of thought, well, you know, thermohaline means temperature and salt. And if you either change the temperature gradient or the salt gradient of these ocean cycles, what if they stopped? The perverse impact is that Europe would get colder. And so that, after he made this kind of wild projection, a number of people say, wow, could this really happen? The latest opinion is they don't really think it could happen in any immediate way. But they the concept is not wrong at all. And the other thing is, as all that Arctic ice cap is melting, the Arctic Ocean salinity is going down. We know that absolutely. All that fresh water is melting in the Arctic, and so it's getting less salty. We don't understand enough about those thermohaline mechanisms to know when that could shut off. You know, these are just huge body of water. And you know that ocean circulation graph I showed, it's really slow, but it's huge. So it's huge and slow, and so I don't think we understand entirely enough, but we don't think that's going to happen anytime soon, even though it's a great theory and got everybody excited. Yeah.
I just want to tell you, we were at Vandenberg Air Force Base when your satellite went up.
All right, when
And,
the Terra on December 18th?
Right, we were there. And
All right.
I want to ask you, though, is your satellite in its 5 years, has it been measuring cloud cover and albedo?
Oh yeah.
And
Oh yeah.
what's the trend?
There's a whole atmospheric science team on our satellite, and I don't talk about them because they don't talk about our stuff. So no, it's a big enough satellite that there's whole teams. This is part of where we see that it appears like the cloudiness in the Amazon appears to be going down, is partly from these trends of cloudiness and aerosols. And so we actually like to hook together about 3 different satellites to get a 20 to 25 year time series. Ours has only been up 5. But absolutely, there is a whole atmospheric science team that is looking at the things you're talking about. The albedo is one thing that we think is causing this March warm-up. When you melt snow, snow is about the highest natural albedo there is. And when you go from snow to dirt, you've basically gone from about 70% to 10%. And so we really think that's part of the feed-forward effect that's warming March temperatures faster.
When we see the rate of increase of the temperature and the CO2, and that rate, if provisions were made to stop the reason for all this, how would the rate going back the other way go? Would it go down as quickly, or does it take a lot longer?
See, this is the question that makes this maybe one of the finest political experiments of our lifetime. Because, and a lot of climate scientists don't like to say this out loud, but it's the truth. And we know now, absolutely it's the truth. If we stop tomorrow, if we all got bicycles tomorrow, we know that the Earth would still warm up another degree from what we've already loaded of heat content in the ocean. If we stop tomorrow cold turkey. And so imagine this political conundrum that we're asking society to completely change its energy, its entire energy path, and yet if you do it, we won't be able to measure the difference anyway, but we still think you ought to do it. And it's only going to benefit your children and grandchildren. And yet that's the blunt truth. Nothing we do in the next decade, no matter how good or how bad, nothing we do will be detectable, because the Earth system is that big and the inertia is that high. What we really are looking at is what happens 50 and 100 years from now if we don't slow the momentum down. And that's when we go from 2 or 3 degrees to 8 or 10 degrees. But I can't lie to you. In the next decade, nothing we do will matter one way or the other. And how you tell a politician that with a straight face, I have yet to figure out. Because with a 4-year time horizon for every decision you make, the minute I say that, they just lose interest right away.
I've been hearing that we only have about 10 years to change things around before we get into, feedback loops. Do you agree with that?
We're already in feedback loops. We don't. The politicians, and Tony Blair particularly, had big pressure on us last spring, a meeting in Exeter, England, where he sent a whole couple hundred of the top climate scientists in the world and locked them up and said, I want you at the end of the week to come out and tell me what dangerous interference in the climate system is. That's all I want to know. Because as soon as you tell me what's dangerous, I'll get to work. And the minute you put an adjective like dangerous on, that has a societal value judgment attached to it that as climate scientists we can't measure. And so we can't really tell what's dangerous. That's something that the social scientists will have to help decide. Because to some people, the fact that all our ski areas may be out of business in 30 years here in western Montana, they could care less. They want to grow apricot trees. And so they'll say, no, I don't think it's dangerous. My apricots are doing great. And so I'm supposed to say that, yeah, in 10 years it's going to get dangerous. That's what the climate activists want the climate scientists to say. And yet we already assume that things that are already happening are dangerous. We think the hurricane trajectory is already dangerous. We think the wildfire trajectory is already dangerous. And so it's sometimes nice to try to put some peg on the board like, we better get going in 10 years or it's going to get dangerous. But that doesn't really hold up to scientific scrutiny. Dangerous is this continuum that we're already into.
So given that atmospheric CO2 concentrations are what's driving this, when you go to your scientific conferences and after the conference you go out with your scientific friends and you have dinner and you sit around the table and you talk about these things, and are there any schemes that you can talk about, harebrained or otherwise, that
that's our specialty,
that folks have come up with in order to resequester this carbon, all of this carbon that we have put into the atmosphere? Is there a way to put it back into the earth?
That's one of the things being worked on. And if you read anything about what we're going to do about this, the first thing you figure out is no single activity will be big enough to solve the whole problem. We're going to have to go to a whole spectrum of new activities that start with wind turbines and end up and nuclear power. And I'm not popular when I say that, but I can't see any other way. I'm sorry. There's CO2 sequestration experiments going on where you burn the coal and then sequester the CO2 in the stack and pump it back down underground. It's actually very good for then getting more oil out of the rock formation. It takes a whole bunch of your energy to pump it back down. So your net energy gain is being eroded in the energy it takes to do that. But I suspect we'll be doing it in certain circumstances once they figure out how to do it and where it's viable to do it. So I think that's going to be one of the things that's going to come along. Now, our beloved president in a State of the Union address even kind of inadvertently stumbled onto one of the ideas that's now getting somewhere. When he said we're addicted to oil, and did you hear the next day the White House press corps tried to say, no, he didn't really mean that. He flubbed his cue card. For once he got something right and then they discounted it. I love it. But what he was referring to is getting a whole lot of buzz right now, and it's called cellulosic ethanol. The first round of ethanol production plans were designed around growing corn and then turning corn into ethanol. And a number of very comprehensive input-output analyses came to the conclusion that you'd use about as much energy to grow and harvest and drag the corn in and turn it into ethanol that you were going to get out of it. So you're getting a net of almost nothing out of growing corn. What's coming along now is the idea that if we could use any sort of cellulosic waste, which is what some people call all the forests around town here, that if you could digest that with cellulase enzymes, then you could use any of a whole big spectrum of cellulose plants, biomass, that you could then distill into ethanol. And what they're actually, the gene jockeys are going wild now trying to figure out how to build the enzymes. I guess the deal is, I'm not real good at this, you probably know more of this chemistry, this is getting closer to your life, but they're trying to see if there's potential to mass produce these enzymes and generate this digested cellulose as an ethanol product, which then, rather than growing a crop, then heck, we might have a way of improving our forest fuel problem here. If we could thin all the fuels in our forests that right now are not commercially viable to haul out of the woods, and we could digest those into ethanol, maybe we could get somewhere. I have yet to see, well, this is getting a long ways out of my field, and it's being talked about a lot. There's literally every month there's new things coming out. And so it's a hot idea, but it isn't ready for prime time, which incidentally, another one not ready for prime time is hydrogen cars. So we're going to have to basically try every single thing we can think of to close the gap on what we need to do. And we need to get going right now. And what's unfortunate is the inertia in our country, because in other countries they're going gangbusters.
I think it's getting kind of late, so maybe I'll curtail the questions here, although I can add that we just had a speaker at our noon seminar today considering for a position here at UM who gave a talk on cyanobacteria to work on cellulosic production of fuels. So we just have been talking about that in our own department.
Oh, yeah.
Isn't it marvelous how Steve can take such complex data and make it so clear? Now I know why he's got such a reputation. So let's give Steve one more hand. And I can remind you that next week we're going to have Professor Dan Reisenfeld talking about the life and the death of the sun. I didn't know the sun had any problem with coronary arteries, but maybe he's going to tell us that that's not so.
Now that's one issue we're not worried about, the sun going out.
Thank you. Safe trip home.